So now we are ready to start, and I can officially say welcome to the Tech Talk for wide bandgap, and at that time the GaN session. So GaN is very important as a wide bandgap, mostly used in the lower voltage region of applications. So we had the silicon carbide just before today, and yeah, what can I say? Fall is approaching fast, and Indian summer shows the first signs here in the northern hemisphere. I see the first trees turning to yellow, and that's also a sign that Thanksgiving is not too far from now. The last articles in my magazine are the ones that made the roundtable talk here, and we have a nice auditorium already, what I see, and so we're ready to start with the first questions. So the first question addressed to Alex and Marco is about what applications do you see getting the most benefit from motor drives using GaN technology?
Yeah, so we're seeing the clearest benefits in brushless DC motors, particularly in input voltage ranges from 24 to 150 volts. 24 and 48 volts are becoming very popular in robotics, as well as in small e-bikes and things like that. We're seeing 96 volts starting to get adopted by these micro EVs, delivery vehicles, or kind of substitutes for the last mile with people. So in warehouses, I think that you see these autonomous robots. They're mostly going to 48 volts, and I think we've also seen a huge uptake in a small market of medical electronics. And one other area that can't be ignored is space. Every satellite has a bunch of reaction wheels to gyroscopically maintain their orientation in orbit. And we're selling, tens and hundreds of thousands now of devices into motor drives for those reaction wheels, because GaN devices are very, very radiation resistant.
Thank you, Alex. So the question to Juan from Infineon is, in the article you show that GaN is offering better efficiency in an LLC converter than silicon. What are the main parameters and characteristics of GaN contributing to this performance improvement? And how would the device behave in a hard switching topology?
Yeah, so these are two questions addressing two types of topologies, hard switching topologies, and another example of a soft switching topology like the LLC. In this article, we were focusing on the differences when the devices are applied on the secondary side for this LLC. So what parameters can be attributed there to this efficiency improvement? From an LLC perspective, as usually in many situations, they are operated above resonance. So you have some hard commutation of the diode, and therefore you have reverse recovery charge for silicon devices that is absent for gallium nitride. So that's one clear advantage of gallium nitride. So all those recovery charge losses are completely eliminated. The second aspect I would like to highlight is the lower output capacitance. This COSS, this lower output capacitance is also reflected to the primary side, and it adds to the capacitances on the devices of the primary side. In other words, it makes more difficult to achieve the zero voltage switching transitions on the high voltage devices on the primary side. So it makes easier to have this soft switching behavior over the wide range of input voltages and output loads. That also allows you to design your magnetics in a more efficient way to increase the switching frequency of the converter, therefore also reducing the magnetic losses because you are reducing the core sizes. So these two aspects are the most important ones that I would assign to the performance increase in an LLC. Now, in a hard switching topology, like the 48 volts down to 12, here we have a different set of aspects. If we are talking about the secondary side, again, I would highlight the reverse recovery charge, and here you will always have this hard commutation of the diode, so no reverse recovery charge, and those losses are gone. I would also highlight the COSS, and now if we move into the devices of the primary side, then you have the switching losses as an important contributor, okay? And those can be related to QG and QGD, mostly QGD. So the devices, especially on the primary side, are able to switch in a much faster way. So therefore, you are reducing the turn-off losses, which are related to QGD. And for the turn-on losses, again, you have the output capacitance. So for hard switching topologies, if we are talking about the secondary side, COSS and reverse recovery charge. If we are talking about primary side devices, the COSS again, and the gate charges, QGD mostly.
Thank you, Juan.
Bodo, can I just add one quick thing? You know, I think
Yes,
that we're
go
seeing
ahead, Alex.
the LLC topology is by far becoming the most popular in servers because of its very, very high power densities. And we're seeing the hard switching topologies becoming more popular in the new DC buses on cars. And one of the reasons is because the hard switching topology is more it's more straightforward to make it bidirectional.
Thank you, Alex. The question to Nexperia: how do the Nexperia GaN FET switch with such a low ringing?
Thank you, Holger. So let me start with sharing a slide first and show you to everyone else that don't know how Nexperia GaN switches. So we can start from the slide. Can you see the slides here?
Yeah.
So you can see here, actually the Nexperia GaN FET's switching waveform, that's a turn-off waveform. And this is a comparable silicon waveform. So as you can see here, the Nexperia GaN FETs actually have little or no overshoot whatsoever. So you have a 400 volt DC bus voltage, and the GaN FET is switching with a ringing of less than 20 volts. Very damped oscillation. There is almost no oscillation whatsoever. Whereas when you compare that to a silicon device, which is same RDS(on), you can see that the switching performance is far worse. And this is, you can see here that the ringing goes to about 500 volts, and then it oscillates quite heavily. So this has a big impact on efficiency. It has a big impact on the switching losses on EMC as well. And it makes the design even more complicated. So to answer the question, how do we do that? I think it's very intrinsic to our technology. So to show you that, we have a slide here. Actually, it's not. So this one, if we go back to this one, so we have a cascode architecture. So our GaN devices are with two devices inside. So you have a 2-die package package device. So you have a silicon MOSFET in series with the GaN device. And by tuning the silicon MOSFET to have a certain capacitance, the MOSFET almost acts as a filter. So this filtering to the signal, to the gate signal that you're providing, makes the waveform be really, really smooth. So, and this is achieved by controlling very well how we design the two together. So we design a silicon MOSFET together with the GaN FET, and we match them in such a way that whenever the device is turning on and off, it is done in a very controlled way. And in this controlled way, you see that very nice waveform that is actually happening out of this cascode architecture, and the combination of the use of silicon MOSFET and a GaN FET together. Thank you. So
thank you.
May I add one comment regarding the spikes behavior, because I think this is a general characteristics also of gallium nitride. In general, they tend to show lower spike levels and a lower level of oscillations and highly attenuated. And I think this is generally due also to these lower capacitance. Then the oscillations, the frequency of these oscillations is higher, and they naturally attenuate earlier because of the effective AC resistances in the rest of the system, in the rest of the layout. And also, I think another important factor, which I think is general across different gallium nitride technologies, is that if we think about the linearity of the output capacitance, that is, if the output capacitance is remaining constant across the whole voltage range, you tend to have less spike levels. Okay, and that's indeed the case for gallium nitride technologies compared to silicon. How much more linear than silicon is, of course, will depend on the technology and will depend on the voltage class. But I think that's also another important factor contributing to this lower level of oscillations.
Definitely, and there is another thing actually that, for example, the QRR, which is the reverse recovery charge, the fact that all GaN devices don't have that, really, especially at turn-off and hard switching, you have the QRR contributing to the higher spikes with the inductance. So you do get quite a lot of benefit because GaN intrinsically does not have any reverse recovery charge. So you only get the very low output charge that the devices have.
Thank you.
Let me ask Marco to answer this one.
Yeah.
You need to unmute.
Hey, Marco.
Okay, now I can. Okay, so what is the benefit of having a higher switching frequency on the motors? Is that with a GaN inverter, we can switch faster. And switching faster means with lower power loss in the inverter. So we can definitely reach the 100 kilohertz and even above. And this has several effects on the motor and on the system. So first of all, the motor itself becomes more efficient, because if you increase the frequency at which you operate the motor, the PWM, then you get lower power losses. And second, you get, if you have in a typical condition where you have, for instance, a DC source like a battery, and then you have cables, and then you have the inverter and a motor, increasing the PWM frequencies is going to reduce the ripple of the voltage in the input and also the ripple of the current in the input. That means you can reduce the typical filter you have at the input between the battery and the inverter. Usually the filter is made of an inductor and capacitors. Sometimes the inductor is not present, sometimes it's needed. And capacitor usually are electrolytic capacitors. And in conventional motor drive inverter designs, which are operating 20 kilohertz, with MOSFET you may go 40 kilohertz. Usually the electrolytic capacitors are not really sized because of the need of the inverter. They are sized because of the RMS current which is going through them. And when you start going 100 kilohertz or slightly above, then you can switch from electrolytic capacitor technology to ceramic technology, and then you're not longer linked to the RMS current flowing in the capacitors. And moreover, the sweet spot for the equivalent series resistance and impedance of a capacitor for ceramic technology is in the 100 to 200 kilohertz, where you get really the minimum of the impedance. So there are several factors making the overall system more efficient. So usually you have to include, obviously, in this efficiency calculation, everything from the input filter to the inverter and the motor.
Thank you, Marco. So do GaN devices have different driving requirements compared to silicon? What characteristics of the ICE driver family are specially designed for driving GaN devices? That's addressed to Juan from Infineon.
Okay, thanks for this question. So do gallium nitride devices have different driving requirements? Certainly they do have some special or driving requirements that you need to pay attention to. What those driving requirements are going to be is going to change a lot on the concept, on the gallium nitride concept. It's not the same cascode concept like the one from our colleague Ilian, to a low voltage or a P-GaN based concept, which is basically a voltage driven device. And in that sense is very similar to any MOSFET, any silicon MOSFET device. And again, for high voltage devices, and I'm thinking about the Infineon high voltage devices, we use the GIT, that so-called GIT concept for gallium nitride, which has inherently advantages for higher voltages. And there you would have also different driving requirements where you would like to have your driving voltage a little bit below 0 volts to achieve faster transitions, especially during turning off. So we have to consider these different technologies for gallium nitride with respect to low voltage, or the choice of technology from Infineon for low voltage is the so-called P-GaN concept. Is normally a voltage driven, it's a voltage driven device. So it's like a usual silicon device, a usual MOSFET. The only thing is you need to pay attention to not exceeding the maximum rating, certain maximum ratings at the gate. And those maximum ratings are around 5.5 volts, 6 volts typically. And that's basically because if you exceed those ratings, then what you have at the gate is basically a diode, okay? And there is nothing stopping the current and then preventing the current to flow there. And that's what could lead to issues with the device. So one area to pay attention to is the driving voltage. If we're talking about low voltage devices or P-GaN based devices, not to exceed the maximum ratings. And therefore, the combination with properly suited drivers, or drivers specifically thought to be able to clamp this maximum voltage, so you never exceed those maximum specifications, is important and is helpful. So now talking about the ICE driver family characteristics, yes, the ICE driver family is looking into that. There is a family of drivers addressing gallium nitride, both for high voltage and for low voltage. Now talking about the low voltage, medium voltage, 100 volts, and so on devices. So we have that clamping feature implemented. There are a couple of characteristics that I think are very interesting. And one is related to a very pull current capability when the gate is a very low level. Why is this important? This is related to induced turn on or return on, okay? So gallium nitride devices can switch very fast, which means that yeah, you need to pay attention to the layout. You need to pay attention to yeah, these parasitics in the circuits. And sometimes this return on cannot be fully optimized because of these limitations in the layout. Therefore, if you have a driver with a very strong pull current capability, when the voltage at the gate is very low, then you can keep your gate low, and then you avoid this return on. Of course, what you need to do, what you need to make sure is that the Miller ratio of your technology has a good value. That's the ratio between the QGD charge and the charge that you need to go to reach the threshold voltage. And that's for sure optimized and is below yeah, a certain value that in principle ensure that you would not experience this return on. So technologies are taking care of that, but still under non-ideal conditions, that could be a help. And the other topic I would like to highlight about these ICE drivers, and it's also related to the necessity to deal with non-ideal conditions regarding layout. Sometimes one would like to do the layout in a perfect way, but other circumstances prevent you from doing it. To avoid this return on, also, these drivers have the capability to drive the devices with negative voltages. That means that instead of going to 0 volts, they can go to -1, -2. Actually, you can select the voltage. So that allows you to have or to avoid this return on, this induced turn on, under a wide range of different conditions, non-ideal conditions regarding layout, etc. So pretty much, yeah, is I would dare to say it's pretty much making impossible to return or to suffer from this return on, and it's very helpful in, as I said, in those cases where, yeah, the ideal or the perfect layout is for whatever circumstances really not possible. Okay. That can be the case sometimes in certain motor drives applications. That can be the case even in higher switching frequency applications, like I can think of a telecom brick converter. Normally the devices tend to be on the top side of the board, the driver on the bottom side of the board. Sometimes it's not easy to have the perfect layout. Under those same circumstances, these two things, the strong pull current capability at low gate levels and the negative driving voltage capability can be helpful.
Thank you. Are there any particular EMC precautions to be taken with GaN?
Maybe I can take this one first.
Please.
Thank you. So I can speak only about the Nexperia GaN devices at the moment, but for them, they're actually improving EMC. As you saw, because the device is switching in such a clean way and smooth way, you'd actually improve your design by designing with the GaN device. So you'd actually make it better in terms of EMC. And we also have a third-party paper which was written by a third-party person engineer that was comparing silicon against GaN devices in EMC. So he had a bad design which couldn't pass the EMC standards, and then he redesigned and put our devices in, and the actual equipment started passing the EMC tests. So in general, for our devices, they can only improve it. But of course, for EMC, you'd always have to be careful with your design, with your layout, and ultimately, that's what's going to drive how good your EMC performance is.
So if I may just add to what Ilian is saying, there's some fundamental reasons why GaN is actually quieter than a MOSFET. And I think that's the comparison here. A bad layout and a bad design can always be noisy. One of them is that the GaN devices are much smaller, and therefore the antenna effect of the layout is much less. And that's actually a significant factor, especially at higher frequency design. Secondly is the GaN devices do not have a reverse recovery of a diode. Now the Cascodes have a reverse recovery, but it's very small. So it's almost incidental in this whole discussion, but GaN FETs do not. And the reverse diode recovery in a MOSFET, if it's used in the circuit, creates enormous amount of ringing and noise. So that is also eliminated. And the third thing, which I think people are a little afraid of, is the faster switching means that you have faster rise and fall times on your device, but that doesn't necessarily mean that there's more energy generating EMC. What it does mean is that the frequency is shifted to higher frequencies. And the point where the energy starts dropping off is at higher frequencies. So you need to be a little bit careful about that, but in general, the filtering of that component is pretty low cost and straightforward.
I would like, I totally agree with everything that was said here. I was thinking that another factor contributing to lower EMC, which is helping, is also related to this more linear output capacitance that you have with gallium nitride. So with silicon, you would tend to have a transition where you start with slow speed, slow rate, DVDT rate, and then it can go very fast, very quickly. So when you translate that into the frequency domain, it means that you generate frequencies over a wide range. Okay. While if you have this cleaner transition, certainly, as Alex said, you will have a frequency component that is very well defined, but very low noise generated at all the different frequencies.
You know, I think there's another effect I'd like Marco to deal with, and that is the DVDT effect in motors and how MOSFETs versus GaN are compared there.
That's what I wanted to add. At the end of the day, in the motor drive, this, let's say, better linearity of the COSS is helping in shaping a better the DVDT. So usually in the motor drive application with a 48 volt, 96 volt DC bus, I never exceed 10 volt per nanosecond, which is quite common in motor drives. And I'm getting very, very nice linear DVDT. And so the two main contributions for the EMC are on one side, the DVDT, which is better in a GaN inverter. And the other side, it's the DIDT, which is in cause, let's say, the cause of the reverse recovery when you have an inverter with diode, which at the end of the day, you don't have if you have a GaN inverter. These are the two reasons in motor drives why you have less generation of EMI and EMC.
Thank you, gentlemen. Here is the next question. So, operation reverse conductive mode during a dead time, since there is no diode, there is higher conduction loss. How this can be minimized?
I think the most straightforward way to minimize it is lower dead time. Don't use the conduction as long. Many people with MOSFETs are used to, waiting 20, 50, 100 nanoseconds for the diode to recover because it has minority carriers in it. In GaN, there's none. So reduce the dead time as much as you can. With these sort of new generation of drivers that are more precise on controlling dead time, you can get dead times in the low nanosecond range, where the losses from the forward conduction of the GaN diode are negligible. So it's very possible to manage that whole story.
I will add one thing which is really specific to motor drives. In motor drives, usually, even low voltage motor drives, the dead time is conventionally used because it's a kind of a habit. But if you're using a gallium nitride inverter, you can, by bracket, eliminated that time. So instead of having, I don't know, 200 nanoseconds, 400, 500 nanoseconds at time, you can easily work with 20 nanoseconds at time. So you have a negligible effect. And there's another thing which is really impacting the motor. The dead time is responsible of two harmonics in the current, which are the fifth and the seventh harmonic. And these harmonics in the current, they convolute in a sixth harmonic on the torque. That means that time in motor drive is just responsible of vibration and heat. It's not making any motion. So if you remove that time, the same exact motor becomes more efficient simply because the sixth harmonic in the torque disappears and all the harmonic, let's say, which are creating vibration are diminished. And then if you have the same RMS current in the phase, you're getting more torque from the motor. And that's one of the main reasons why switching from MOSFET to GaNFET in a motor drive, then you get a more efficient system.
Maybe I can add here just because our technology is quite different from EPC and Infineon in here. Just I'll share a slide to show you again. So just to explain, in our case, actually the conduction in reverse is very low because we have that 30-volt silicon MOSFET in here. The conduction losses are actually minimal. So you have the equivalent performance of a 30-volt silicon MOSFET. So you have only 1.3 volts at 12 amps reverse conduction. So at 20 amps, you go to 1.5 volts. So it's really negligible. So in this case, you can have the benefit of having this high performance 650 volt GaN device. And at the same time, in reverse conduction, you'd be able to afford to have higher dead time. For example, as Alex mentioned, 50, 100, 200 nanoseconds, and it won't make a big difference. Because actually what happens is in reverse conduction, you're forward biasing the diode here, and you're making a connection between the gate and source of the actual device, the actual GaN device, and you're effectively turning on the GaN device. So you have only the actual diode voltage drop, which is very, very small.
Yeah, Ilian, I don't know if you meant to this, but if you use very long dead times, it actually has a very negative effect on your circuit efficiency and also on noise generation.
No,
so
of course.
I don't recommend that.
On the motor efficiency also, the motor gets less efficient. That's why we say if you go to gallium nitride inverter, then you eliminate at that time, and then the motor, the same exact motor becomes more efficient in the same exact conditions.
No, that's correct. But let's say in other applications, you can probably afford to have at least some dead time and still not compromise on efficiency with our devices.
Thank you, gentlemen. What's the recommendation for short circuit outstanding time for GaN-based applications for motion control segment?
Can I take this?
Ilian, go ahead.
So first of all, then Alex can then comment a little bit better than about the ruggedness under short circuit of our gallium nitride EPC GaNFET. But on the application, I'm following the typical rules where there are basically a time that you have to wait to assess that it's a real short circuit and it's not just a capacitive spike. And then you have to act and open the short circuit in the conventional mode. One thing you need to take care if the way you switch off the short circuit. So first you usually have to let's say react within 3 microseconds nominally, but there's no limit like IGBTs. There is no limit like 10 microseconds or something like this. It's really energy limit. But one thing that you have to do in the inverter, it may be that in some cases you don't have just to switch off completely all the gates, because then in that case you would have the current short circuit current recirculating in a reverse conduction mode that could be a little bit detrimental. So you may decide with the controller to have a different way to switch off the short circuit, like it's done in some fun application where you switch off 3 of the device, for instance, the high side device, and you keep on for some moment the low side device. But that's not really mandatory. So it's really similar to what is done today with the MOSFET.
Yeah, I mean, we've done massive short circuit testing on our MOSFETs, and I just want to say that these are all below 400 volt MOSFETs, and they are far more rugged than our GaN devices are far more rugged than conventional silicon MOSFETs, and that's partly due to the fact that wide bandgap semiconductors are able to go to higher temperatures before they fail. And all this data, by the way, is on our website in our phase 12 reliability report.
Thank you. Thank you, Alex, for additional comment. That's to Ilian about SMD portfolio.
Yes, thank you. So I'll just bear with me a second. So thank you for the question. So in here, can you see my screen, by the way? Moment.
Yes.
Showing our current portfolio. So at the moment we have 2 products released in 2247, and some of the data that you have already shown you on the very smooth switching was also on these new devices that we're bringing. It's a new copper clip package, which is going to be both available in bottom and top side cooling. We will release our first devices in this package in Q1 next year in 33 milliamps, 650 volts. Again, they will be available in bottom side, top side cooling, automotive and industrial grade. Then we're looking to expand the portfolio to even lower RDS(on), where you can go to, let's say, 5-10 kilowatts and more with the devices that we're releasing at 13 million, again in that CC package, which will be very, very good, just because that option to have it as a top side cooled eliminates the PCB in between and makes the thermal connection to the heatsink a lot more better, and you can get really the full potential of the power density that GaN can offer. And also, of course, in the future, we'll also increase the portfolio to higher and even lower RDS(ons). But for now, the main target for next year is to release these 2 products, the 33 milliamp and the 13 milliamp, in the several variations, industrial and automotive. Yeah, thank you. I hope that answers the question.
Thank you.
Now, if I could take that one, you know, what's
okay,
the
Alex,
VGA
go ahead.
format for GaN devices? Since all of our devices are chip scale, they're both BGA and LGA, which has bars instead of balls. You know, I think that we have a lot of experience with that. If you get much beyond about 500 volts, you start getting into problems of a chip scale package and creepage distances, that they become so large that the chip becomes much less efficient. So I think that when you get into 600 volt devices, they should be packaged. When you're below that, the package only takes away performance.
Okay.
Here, I think if I may add, yeah, I think it also depends on what are the creepage distance and to what creepage distance regulations our customers or the customers want to adhere. And it certainly, we see different, different regulations. So here, with respect to inherent limitations of BGA, I totally share what Alex said. Now the question would be on what are these creepage distances that the customers want to implement for 100 volts up to 200 volt devices? And inevitably, they can also, if we adhere to very strict creepage distance regulations, inevitably lead to necessarily higher or larger packages. In the case of chip scale packaging, it makes it very difficult because then one would need to limit the number of VGAs. So here I think that chip scale package, that's my particular opinion, is certainly a great option, and it's going to be unbeatable in terms of the power density, because basically there is no package around it. I still see the challenge of some customers that want to have this 0.5 millimeters distance, 0.7 millimeters distance for 200 volts, even at 100 volts. Ideally, one could get around that. If not, I think there is certainly a space for some other type of packages, QFN-based packages, innovative packages that add very little parasitic inductances. Certainly, it adds a little bit of size. So I would say that the limitation is in the end coming not so much from the technology itself or the packaging or the VGA technology. It's more from the restrictions each customer decides to deal or to design with in their application.
Yeah, I agree with that.
Yeah.
I think that's well said.
Yeah, definitely. And for example, when we were designing our CC pack packages that I just showed you, that's what we were taking into consideration, because really what different manufacturers adhere to. So, for example, every industry would have a different standard, but we found actually a common denominator between all. They were all looking at the pollution levels. Again, it depends on, for example, in our cases, on the package mold compound and what CTI rating that mold compound is. So it has quite a few things to look into and then actually decide on the actual creepage that you need for the certain device.
Thank you, gentlemen. The next question is up.
So I think I can take this.
Okay.
So if you just consider a typical MOSFET inverter, usually it is designed around 20 kilohertz or 40 kilohertz to have 98% efficiency. So when you do a similar inverter with a GaN FET, you can go up to 100 kilohertz, still get 98% efficiency. So what's the point? The point is on all the rest, the input filter and the motor. The motor becomes more efficient, the input filter disappears and becomes smaller. So the overall efficiency becomes higher. And that's the main important point regarding using gallium nitride within motor drives applications.
Okay, Marco. So top side cooling device comparing to bottom side cooling, it would quite difficult to provide low RTH case heatsink on the board with multiple transistors, since due to the PCB warpage heatsink surface not flatness, that requires a higher RTH thermal interface material, resulting to higher RTH overall. So
I can take this one first, I think,
go,
because
Ilian.
yeah, we have the top side cooling device, and we get these kind of questions quite a lot, actually. So in general, so the PCB is around 2 kelvins per watt. I think that was roughly what the actual thermal resistance would be. And then you have, on top of that, you have the actual thermal interface thermal resistance as well. So that goes to probably 2.5 to 3 kelvins per watt. And then you put the actual thermal resistance of the device. But when you have the topside cooling, even though, let's say, you would have to compensate for some warpage or some surface unevenness, which is also not as much because we have quite tight tolerances on the devices. So you wouldn't have that big of difference to actually compensate for. So you would have a very low thermal resistance of that thermal insulating material, even if it's, let's say, worst case scenario, 1.5 kelvins per watt. Still, that would be much better than what you can achieve with the 2 kelvins per watt which you have from the PCB, and then on top of that the thermal insulation material and then the device.
Yeah, if I could add, when you have a package, it tends to confine the heat around the semiconductor. So the most efficient thermal package in the world is no package.
Exactly.
And it's one of the reasons why chip scale packages, we focus so much on chip scale packages, because they basically take a very small die, which GaN is much smaller than silicon, and it allows you to extract more heat out of it. So we're finding that you can get about 4 or 5 times lower thermal resistance for the same area for a GaN device. And because it's smaller, it is less sensitive to these tolerances that people are talking about, PCB warpage. So I'll just flash up an image here of the kinds of results that we get and our customers get as well. So let's see here. So you can see here, this is a 4 square millimeter die. I'm showing you the sim picture because it's not very interesting to show you a photograph of the outside of a heat sink. But this is a 4 square millimeter die, and it's got 4 degrees C per watt. So you can't do that with a package. You just can't. And one of the big advantages, again, there are no interfaces, and you can get heat extracted out the sidewalls. And sidewall area, when you get very small, is actually quite a bit larger than the top or the bottom surface. So really, there is almost a miraculous ability with chip scale devices to extract heat much more efficiently than ever before.
So maybe I can add to this. Actually, I think Alex, this is very good for your devices and your the power range that you're aiming at. But for example, when you look at our devices and the package that we've designed, so the package is a copper clip package. And if I can share just a picture of the package, you can probably see. So if we go back to the portfolio, maybe just to extend this package to show you this. So you can imagine the device sits somewhere around here, and it's actually smaller than the heat tap that you have here. So, and because it's a copper clip package, in our case, there is directly soldered to the silicon and to the GaN devices. So this provides almost like a heat spreader that is a lot better than you'd have just with the chip. So for example, virtually the thermal resistance of copper is very good. So you don't have an addition to the thermal resistance. And what happens here is not only you have that connection, but that connection allows you to put pressure on the package. So that pressure means that you can put a bigger heat sink and you can actually not be constrained, because when you have a die and you try to put a heat sink on the actual die, then you wouldn't be able to put such pressure as you would be able on a package, just because the die will crack before the package. For example, the package can sustain a lot more pressure, and therefore I think for the field that we are trying to aim, the multiple kilowatt powers with GaN, this is the right way to go.
Yeah, I mean, look, at high voltages, you need a package. So I cannot in any way disagree with you. The only thing I can say is that the amount of pressure you can put on a package with multiple interfaces is less than the amount of pressure you can put on a chip scale package. We have that evidence also in our reliability reports. So there's that added flexibility.
Thank you, gentlemen. Is there any motor type that's going to benefit more due to the use of GaN?
Marco, what do you think?
Yeah. And so the motors which have low inductance. So if you have an idea, for instance, hadrons motors, cobalt joint motors, all those motors that need to be to be very small, so miniature motors, but in the dimension they need to exhibit quite good dynamics and also high torques. So this type of motors usually have less material in terms of winding turns, less copper, and have less iron. Then may have better magnet, stronger magnet, but less iron. At the end of the day, they come out and being in the micro Henry inductance range, and they are terribly difficult to be driven. And already with MOSFET inverters, you need to go in the 100 kilohertz range to drive them in a proper way. But the 100 kilohertz range becomes a problem for a MOSFET inverter, which start to become extremely lossy. So all those type of application where motor are becoming essential part, like in e-mobility, especially light e-mobility, where the weight is really important, then the material becomes less material, and then lower inductance, and then when the inductance becomes smaller, you need to have higher frequency to get the best of the motor. And then you have to have an inverter which can handle that higher frequency.
Yes, exactly. So, and I would say this, and we have seen, or we are seeing a renewed interest of customers in this ironless, that's slotless type of motors, because for some applications like e-bikes, etc. So yeah, the reduction in size is has a very strong value, but yeah, they have very low inductances, and that's where gallium nitride can be especially useful, because then you can have your inverter commutating at a much higher fundamental frequency than you would normally do with silicon devices. So definitely I concur there. So low inductance motors, coreless or ironless type of motors. And those are no new motors in the end, but I think I see a renewed interest in those type of motors. And to some extent, I think is very well paired, and I don't know what is coming first, if it's the coupling with gallium nitride, or gallium nitride finds an excellent companion in this kind of motors. Okay.
Yeah, gallium nitride is becoming definitely the enabling technology for this type of motor, and this type of motor now will be getting more and more applications.
Yeah.
Thank you, gentlemen.
Maybe if I can just add, sorry, Holger.
Ilian.
Hello?
Sorry.
Yes, thank you. No problem. Just to add a more generic answer to the question as well for GaN devices at higher voltage, I think the servo motors in particular can really benefit from GaN devices, just because, for example, in a servo motor, precision is actually quite important. And for example, when you have a gallium nitride and switching at higher frequency, your signal up. So when you have a DC-AC inverters and you have the filtering at higher frequency, then your signal becomes much more pure. So the sine wave becomes really pure without any distortions, and that really helps with the torque ripple. So not only it increases efficiency of the motor because of these less harmonic distortions, but it also gives you that less torque ripple because of these distortions, and your accuracy becomes much bigger with the GaN devices.
Thank you, Ilian. So we have a final question, a quick one. EPC has released an 80-volt monolithic power stage and others 600-volt discretes. There are several advanced gallium technologies already demonstrated in research, such as SOI, CMOS, high-side, complex logic, power topologies. Can you comment on what has a chance to make the leap from research to future products?
Well, maybe I'll take a stab first at that. I think that the future of GaN as a power device is in ICs. I think that GaN is a better semiconductor than silicon for power in general. If you couple that with the fact that it's much easier to integrate than it is for power in silicon, I think that you see these extraordinary benefits. Today we have just NMOS capability in integration, so that's a limitation, particularly in things like quiescent current, but it doesn't really limit functionality. So you're seeing more and more functionality showing up in GaN ICs. We have a whole family of ICs for LiDAR and for half bridges that are either out or coming out in the next few months. And I think that you will see GaN going from monolithic half bridges to full bridges to three-phase bridges to multiple high sides, and all of those functions that today are more challenging in silicon. And that will all occur long before you see GaN in DRAM or something like that.
Thank you, Alex. We are coming to an end, and I'd like to thank you all for your contribution. And I'm looking forward to see you at our Wide Bandgap conference, which is virtually again at the end of November and December. We have all the details announced on the website and starting in our magazine to have that also promoted. So looking forward to welcome you all in November and have an ongoing fruitful discussion for future design. Thank you very much, gentlemen. Bye-bye.
Thank you.
Bye-bye.